All right.
We are live.
All right, perfect. So I'm assuming you guys can hear me good. You can see my screen. Everything's good to go, right?
Yep.
Perfect. All right. So we're going to be covering, I was mentioning that this webinar I'm going to do is part of a bigger technical training course that I used to do. It went for hours. So what I did when Tom invited me in to do this, I pared down an existing presentation and I kind of cherry picked some things out, and I patched together what I think is going to be about 40 minutes of me yakking. And then if we have time, I was told we want to go about an hour. I have a tool that I developed years ago. I made a bunch of updates to it, but it's Excel based. And it does basic system design for a process chiller for you. It does a lot of stuff. So if after I get through this, I'll present what it's all about. And if you guys, in your course of travel and you think it's going to be helpful to you, I'll send it over to Tom and he can distribute it to you guys. You just have to have Microsoft Excel to run it. But I'm going to try and get to that today. So my name is Martin King, and I'm out here on the left coast, just outside of Portland. And you can check me out on LinkedIn. I won't go into my, my life history, but I was a contractor. Well, I was a union journeyman out in California. Went through that whole thing after getting out of Universal Tech. So I turned out as a journeyman. Then eventually I started my own business. So I started out just one truck fixing stuff, and I grew that. I ran that business for about 17 years. I had 33 trucks, something like that. And just by a sequence of events, I got into the process chiller manufacturing business. So for a while, I ran both the contracting and the manufacturing while I was trying to raise a family, and it was a challenging time. Anyway, so I sold the contracting company in 2000. I went exclusively into doing process chiller manufacturing, and I sold that company, Legacy Chiller Systems, in 2020. So I'm retired, sort of, whatever the hell that means. So now I want to put a big framework around what I'm going to talk about. The niche that I was in was strictly process chillers. So the biggest chiller that we manufactured was about 200 tons, but we did, water-cooled, air-cooled, package split, any configuration. We did a lot of OEM work. We had a very big market share. We were really blessed in that. We did a lot of medical applications, a lot of MRIs, a lot of CTs, linear accelerators for cancer therapy, stuff like that. So we played in what we call the mission critical market, and I'll get into that in just a minute. But large tonnage, centrifugal screws, that's not what we did. So I just wanted to make sure that everybody knows where I'm from. So I had to throw this in there. What I'm going to talk about does not negate the need for a professional system designer, right? So what I'm going to cover here will get you in the ballpark, but there's been absolutely no consideration to local code standards and things like that in this presentation. So that's just want to make sure that's spelled out. All right, so what I want to get done today is I want to explain how to get to the correct process chiller design based on the system requirements. So what you want to do ultimately is you want the performance of the process chiller to meet or exceed. I always try to exceed a bit on the thermal transfer, the BTUH transfer, as well as the pumping requirements. So that's the goal. And I want to try and give you some tools on how to do that. Hey, before we go, show of hands, where are you guys? Do you guys work on process chillers?
Yes.
You do? Okay, very good. Very good. Okay, so we're also going to be going over the basics of fluid or cooling medium distribution. And I'm going to present two system layouts that are most common in process chiller applications today. And I'm going to go over the benefits, the drawbacks of each, and take it from there. All right, so what I want to do also is I want to make sure that I impress upon you guys the importance of making the proper selection so the systems run reliably. That's the ultimate goal, is making sure that you figure out what the customer needs. And sometimes they don't know. I was telling Tom, I've had many engineer argue with me about certain things. And ultimately what the goal is, though, is the machine that shows up has to meet or exceed what the customer's requirements are. So what we're going to do is the topics I'm going to cover is understanding your process requirements. These essentially are the questions that you have to have answered before you can actually get into a design for a customer. I'm going to introduce the system design tool. That's going to be at the end. It could just be a quick brush over. If we have time, we'll dig into it and I'll show you how that tool works. Matching the chiller requirement to the process thermal requirement. So that is, I talked about that a few minutes ago. And then the other one is pumping. Pumping is a big deal, obviously. Even if you have a chiller that has enough cooling capacity, you got to make sure that you have enough capacity on the pumping side to get that capacity out to the process load. And that's actually probably one of the biggest problems as a manufacturer that we had, because especially when you're doing change outs, when you're doing a change out on a chiller, you're going to ask questions, and I hope we're going to talk about this some more, but you're going to hopefully ask questions about specifications on the existing pump, right? Because not all pump curves are the same. A 1/2 horsepower pump on a Gould's pump is going to be different than the B&G, right? So and then you get into the whole subject of impellers being modified, all kinds of stuff like that. So I'd say most of the problems that we rarely had problems on the capacity side, but we did have issues post-production right at the time of installation, that there were some numbers that were left out in the calculations of the plumbing system that caused pumping issues. So I'll get into that a little bit more. And then again, we're going to look at the fluid distribution systems. The two we're going to look at, which represents probably 98% of the market out there on the process chiller side, is what we're going to call closed loop or recirc. And then we also have what we call an open loop, which is what we call once through. So, and I've got some drawings we're going to go over in just a little bit. How's the pace? Am I going too fast or too slow? Am I boring you guys at all?
Perfect. Keep it rolling. Good.
You good? Okay. All right. I don't hear any thuds with heads hitting the table, so that's good. Okay. So the first thing you got to do, so what we're going to do is run through a scenario. This could be real life situation where you've got a brewery breweries were the worst, because they're run by, you're working with the brewers and they can tell you how to brew beer all day long, but they really don't understand chillers at all. So you get a call from the brewery, their chiller took a dump, you go out there, the thing's old enough to vote and it hasn't been maintained. I know that's a shock. It hasn't been maintained at all. And you've quickly come to the conclusion this bad compressor that you found is not worth putting a new compressor in a piece of equipment that's got 300,000 miles on it in car terms. So we're going to recommend replacing it. So the problem with that is being so old, the guy probably bought it used to start with. You don't know what you're dealing with. So in order to figure out what the customer needs, you have to figure out what application it is. Now, the example, obviously, that I gave of a brewery is not air conditioning. So I'm going to go through these different types of processes. So you have process chillers that do service buildings for air conditioning. Now, again, that's not super common, but I'll explain a real common application. You have the surgical center. Surgical centers, they tend to be very modular. So we sold a lot of chiller, package chillers to little surgical centers. And they're kind of mission critical, but the reality of it is if the chiller goes down, they can still perform some procedures. So there's, limited impact. They're getting uncomfortable a little bit because the cooling's off, but they're still getting work done. So that's what we call air conditioning duty, climate comfort control duty chillers, process chillers. Then you have industrial commercial. There's a lot of industrial commercial applications that use process chillers. These are typically 24/7 applications, and the difference on this one is if you have a chiller failure, depends on what they're manufacturing, but in many cases, if you had a commercial industrial application and they're using that chiller to cool a process that they need to make whatever they make, they're going to have moderate delays, and it will impact their income if it goes down too long. Then we run into mission critical, and this is the space that my old company played in. So these are your MRIs, these are your CTs, these are, life safety type things. In the realm of mission critical would be an MRI, and a typical problem area is if that thing goes down, if that chiller goes down, the gradient compressor, which keeps the superconductor cool, loses its cooling, and after no time at all, that MRI starts dumping helium, which is very expensive, and it extends the downtime because they just can't load it with helium and restart it and go again. It could be down for days, and some of these hospitals are billing $100,000, $150,000 a day just in scanning income, plus the cost of the helium. So it's a big deal. Okay. The brewery I was telling you about is going to be more of this industrial commercial, right? The brewery, they're going to lose some income if it's shut down too long. Mission critical, it's immediate. They go down immediately. And then there's another category called what I call mission specific. And this is another area that I played in a lot. This is where you have machines that are designed custom for specific applications. Now, I want to bring this up because if you're talking to a customer and they call you and they need a new piece of equipment, and you do your sizing, hopefully you use the tools I'm going to give you today, you figure out what you need, and you start calling around to the chiller manufacturers, and they're like, wow, we don't have anything in our catalog to do this. We'll have to go, we can't help you, or you're going to have to go to a custom house. And I would caution you to make sure that the markups that you use for mission specific custom equipment should be about 10 to 15% more, unless you've done a few of them. They should be higher than all these other three categories, because you will be doing some babysitting, because these custom applications tend to there's a lot of variables, and a lot of them you don't find out about till the end. I was mentioning pumping issues. This was where you would run into that. An example of mission specific, and there's a lot of this work out there, is we used to have an account or have a relationship with Hewlett Packard. We used to build these very, very custom chillers for their digital IC testers. And it literally took us 2 years to figure out what the engineers back in Germany were trying to do. And we went through some pain. Now, it was very, very profitable. I mean, we were building chillers that were costing us $10,000, and we were selling them for $30,000. they were very much in demand, and it's one of those great work if you can get it type situations. But on the upfront side, we had to really price these up in order to make sure that we remain profitable. But it's great work if you can find it. Any questions so far?
Nothing yet.
All right. All right, so the first thing we're going to do is we're going to get the thermal profile. So what this includes is a few things. First of all, we have to figure out what the load at the target is. All right, so this is typically going to be the machine or machines that we want to cool with said chiller. This can be a little bit of a challenge because if you're cooling a piece of equipment that's been manufactured, you are in pretty good shape, because a lot of times the manufacturer that makes that machine, I'm thinking about a laser or a one of these high pressure water cutters, things like that. If it's made here in the US, typically you can open up the site prep guide and find out how many kWh or BTUH is being transferred to the process fluid at max Q, max load. All right, so that's a big deal. Now, if you run across a situation where you're cooling a bunch of plate and frame heat exchangers, that's a totally different story. What I always recommend is when you're in a situation where you're cooling other heat exchangers, secondary, third, tertiary loops, gets really crazy. What you need to do is ask whoever you're working with, whoever is requesting the quote, you want to get what you call the run sheets on those heat exchangers. And the run sheets are basically a document that says, under the design specifications, here is what the rejection is going to be from the hot side of this heat exchanger to the cold side into your application. So anyway, load target, very, very important. And when it comes to the thermal profile, that's a very, very important number. The other one is load variance. Now, some processes, they don't care. I mentioned the digital IC testers from HP. Those things, we were actually cooling another heat exchanger, and they were really complex and fancy. And as long as we gave 54-degree approach plus or minus 10, they were happy. So we had no major issues. But then again, if you have a linear accelerator, which is commonly used for cancer therapy, and you give that plus or minus 2 Fahrenheit, you could have a problem. A lot of times these systems will alarm out at plus or minus 2 above and below the target set point. So learning the load variance is very, very, very helpful. Okay, supply, actually, you know what, I messed that up, guys. Sorry. Load variance has to do with the process load. I'm sorry, I got ahead of myself. So load variance is going to be the how much energy is going from the process into your chiller loop. And what I'm getting at here is that an MRI, that when you're in standby mode, is very, very low, but if they go to a full body scan, it can go up 50, 60, 75% within minutes, right? So understanding the variance will have a lot to do with the design, and we're going to get into that in a minute. The allowable supply variance, that's what I just explained a minute ago, that has to do with the medium, the temperature of the fluid going into the process, and it's the systems or the process at your cooling's ability to deal with it. So like I said, some are very, very tight, MRIs, for example, some are very big. So you have to find that out from the client. Okay, so now that we talked about the thermal requirements, now we're going to talk about the process pumping requirements. All right. So in most chiller applications, there needs to be some type of what we call a system pump. And a system pump's job in life is to take the fluid from the chiller and send it out to send the cooling medium out to the process, bring the energy back and deal with it. So that's what a system pump typically does. Now, in order to size your pump, you got to have this information. Some of it's pretty easy to get, some of them not so much. So you want to know your flow rate. This can be kind of complicated because, again, now you're getting into what the process equipment is requiring for flow rate. So we mentioned this earlier. If it's a manufactured piece of equipment, like a CT scanner or a digital IC tester or something like that, they'll usually have in their documentation, they'll have what the flow requirement in gallons per minute, liters per minute. So that's a really important piece of information. The next one is you want to find out what your pressure drop is. So for example, if you're flowing your water glycol mix, whatever it is, through your piece of equipment at its design flow rate, and let's just say I'm going to pick a random number out of my head. Let's say this requires 20 gallons a minute. At 20 gallons a minute, you may have an approach pressure at 30 psi, but that sucker, the piece of equipment, may have a 10 psi pressure drop going through it. So it's going to go in at 30, for example, and it's going to come out at 20, right? So you need to understand what that pressure drop is. And then you have to figure out, so now that you've got the pressure drop going to your, going through your piece of equipment that you're cooling, now you also have to figure out what your system piping pressure drop is, right? So as that fluid's going through your pipes, it's creating friction, right? It's bouncing off elbows and going through valves and doing whatever it does. That whole process from point A, which is the discharge of the system pump, back to the inlet of the chiller, that whole pattern of flow is going to generate additional pressure drop. And the system sizer does a pretty good job at dealing with this, and I'll show that to you in a bit. Okay, now here's a big one. So this has to do with your safety margin. So once you know your flow rate, once you know your pressure drop, for your process, and you know your pressure drop for your system piping, I recommend a safety factor multiplier of 1.10, 10%. That will, in most cases, that will keep you out of trouble. It's just a smart move. Now, there are some times where this will run you into problems. So I mentioned digital IC testers. Hewlett-Packard was sold to a company called Agilent Technologies. They re-engineered the whole thing. And I found out after the fact, they didn't tell me this, that these engineers back in Germany, they engineer by committee. So the cooling unit, the process equipment that we were working on, made it 3 or 4 different departments there touched it. And what I found out was each department that touched it put their own safety factor in there. And the way that came up in real life was when we were selling these chillers to them for this new latest and greatest design, we would sell them a 15-ton package chiller, specially OEM custom designed for this thing. And the second compressor was never running, no matter what they did, right? So after we peeled away the layers, we found out that we have their safety factor plus our safety factor. We were selling them a chiller that was massively oversized. So sometimes that can get you into trouble, and a lot of times you don't know about it. But I always argue, if you're going to be running into a sizing problem, it's better to be too big than too small. And then we're going to also get into the different plumbing systems, and I'll tell you why on one type of plumbing system we call a research system, you can get away with that, right? All right. Any questions? You guys good?
So far.
All right. Okay, so I hope you guys can see this. I don't know. Can you make this out okay?
Yes.
Okay. So what you're looking at here is the most common type of application for a mission critical chiller. So this represented probably 90% of what we did because we were mission critical manufacturer. So let me explain how this works and the reason why we call it a recirc loop. So this design had three pieces of equipment that we made. We made a tank section that had a system pump. We talked about what those do, but I'll go over in a minute. This was a poly open tank. And then we had two large chillers, right? So inside each chiller, we had a recirculatory pump. So these pumps here, their job in life was to suck the hot water off the tank, put it through the evaporator, and then back into the tank. That's what they do. And then we have a check valve in there that would prevent backflow if one pump was off and that kind of thing. All right, so that's the recirc side of the system. We would equip these with, I don't know if you guys are interested in this, but we'd always equip these things with filter bypass assemblies. Or we put this in the design. We didn't do plumbing, we just did the manufacturing, but I always provided these designs to my clients. So, and this gave them the ability, we had pressure gauges we recommended us installing across these strainers. And when the pressure differential across the strainer got too high, they can close these two valves, open this valve, clean the strainer, and put it back together again. This is a basic filter bypass assembly. All right, so this is the recirc side. This is the system side. All right, so we have our big system pump here. It's pulling off the tank, going out through another bypass assembly, going through here. We always recommend installing a bypass at the end. I'll explain that in a minute. And then it goes back to the tank, right? So you'll see that in this particular one, we just had one. This was kind of rare, but we had some kind of, this is just showing a heat exchanger. I don't remember what this was. I think it was a biodiesel plant, if I remember right. So this is a branch. So basically what we do is we tap off the main supply and return headers through the heat exchanger and then back in, right? So that all that energy that's coming off of here is going back into the tank, right? Now, can anybody tell me what the advantage of this type of thing, of this type of design would be?
Got a lot of windmill effect with the buffer tank in there because you got a lot more fluid in the system.
All right, so thermal fluid mass, that's one, but what's probably a little bigger benefit to something like this that has to do, I'll give you a hint, it has to do with load.
Coupled.
It's what?
I would have called it decoupled, primary, secondary.
Right. So anybody else want to chime in on that? What the benefit of what he said would be?
Multiple temperature ranges for different processes. Also.
No, that's not it. Okay, so what the benefit of a recirc, and that's true, the decoupling, in a lot of ways, I think, yeah, then you said what I'm going to say. I'm going to get a little more detail about it. So I mentioned earlier about thermal variance, right? When I was talking about the MRI, I was saying that an MRI can go from, virtually no load all the way up to full load in just a matter of minutes, right? And that, I don't know what this heat exchanger was cooling, but it's very possible that the hot side of this thing is hooked up to something that has an on and an off, right? So you turn it on, and all of a sudden, bazang, you have a bunch of energy coming in here. So this hot line right here, or the delta T between the two lines, I'm just going to pull some numbers out of my hat, but let's say this is going in at 45, and before they did whatever they did on that load, we only had maybe 47 going back, right? Very depending on the flow rate, but low load. And let's say whatever it is they're cooling, they turn that sucker on, and bang, all this hot energy comes in on the hot side of this heat exchanger, and this 45 is feeding, and all of a sudden this thing jumps up to 60, right? So in that scenario, what's the benefit of having a recirculatory loop?
Not hammering the chillers with that hot water to start with. You still have some windmill effect in that tank.
Exactly. Yeah. It's what I call thermal capacitance. So what happens is that big old chunk of heat, rather than getting pulled directly into the chillers, that hunk of heat is going to mix like crazy in here, right? So they won't see necessarily as big of a degradation on that 45, because that hot fluid, depending on the flow and how much energy it is and the size of the tank, that you're going to see a lot more stability right here based on the volume. So it's mixing with all that volume. That's the benefit of having a I don't know what
plastics plant in that buffer tank, they'll baffle it to where it'll have holes in
Yes.
it. But more
Yeah.
of the warm water stays at the chiller inlet, where the colder water is dumped into the area of your
Right.
system.
Yep. Yeah, we never did that, but because what we would do is we would upsize these recirc pumps so there's so much turn in here. We experimented with baffle tanks a little bit, and we found that we'd rather have just big ass pumps in there doing it. But yeah, that's another way to do it for sure. So
in this example, you've got 2 chillers, but you could have 3 or 4, or you each one chiller, or maybe the first couple stages, could have unloading in the chiller itself too.
exactly. Yep. That's
That's
exactly.
Turn down ratio.
Yeah, that's exactly right. And what it does is it gives you the ability. So in my example here, we got 60 degrees coming in here. It's mixing. Well, what immediately is going to happen, and I may be going off in the weeds here a little bit, both of the controllers on these 2 chillers are going to say, whoa, wait a minute. My set point was 45, and I'm seeing a rapid change here. So it gives time, this extra capacitance here gives some time for these compressors to stage up or load up, if depending on the type of compressor we have in there. And again, the benefit is that the customer doesn't see the degradation. So that's really the big thing. Talking from a refrigeration standpoint, that's also beneficial for your refrigeration, because as you guys know, if you've got a TXV, because most of our stuff was TXV, either an EEV or a regular mechanical TXV, if these evaporators saw a big spike in their approach temperature, let's say we originally sized them for 50 degrees approach coming in on the inlet of the heat exchanger, and for some strange reason now it's 60, the design is a little out of whack. So sometimes you can have, especially on split systems, you can have oil return problems, you can have all kinds of issues because you're running that evaporator outside of its normal spec. So you want to keep stability as much as you can on these chillers. Okay. All right. Any questions on that?
Just out of curiosity,
What's that?
For tank or your surge tank, how much water do you want in the system?
Great question. Great question. So what we would do is we would figure out what size, or excuse me, what the gross flow rate in the application would be. And remember, that was one of the things you're going to collect. So let's just say this particular application here, this little heat exchanger. Let me do a little math here. Yeah. So you want to have about 2.5 times your flow rate. And I'm talking about the flow rate to the entire process. So in the little example I did here, if this loop, the flow rate through here, you're going to have a little bit in the bypass. Let's say that this whole process requires 50 gallons per minute load, the load as well as the bypass. You want to have about 2.5 times that in storage, right? So 50 times 2.5. So you want to have about 125 gallons of volume. Now that volume can come from your plumbing, right? So but that's the calculation that we used. Does that make sense?
Yes.
So the plumbing and the tank and that 2.5 times.
Correct. Yep. Yep. Okay, so that's a recirc. All right, so this is a once through. Now let me see if this will work. Hang on a minute here. Is that bigger on your side?
Yes.
Okay, cool. All right. I saw that link popping up and I'm like, yeah, that's weird. Anyway, so this is what we call a once through. Let me look at this for a second. Something is a little messy here.
Which return. So
Yeah, hang on a minute here. I'm not liking what I'm seeing here. Let me see here. Yeah, it's a wrong drawing. I'll have to stick with this one, even though it's not very good. Okay, so this is a once through design. So you have a chiller. This is just a package air-cooled chiller. Terrible picture. This is one of our pre-manufactured tank packages. In this particular one, and you can't really see it here, this blue thing, this little blue blob here is the system pump. So we've sized the system pump to handle all the current as well as future heat exchangers, what we're showing here, as well as the flow rate for the chiller, because the chiller, based on its tonnage, requires a certain flow rate. So that's what this whole thing does. So in this application, the way it works is this would be, by the way, this would be a pressure rated tank. This particular one is not an open tank. So you're going to have the hot fluid coming out from the process. It's going to go through the chiller. It's dropping into the tank. The tank's connection, or the pump's at the bottom of this tank, and it's shooting that fluid back out through the filter bypass assembly. Same setup, right? You got a supply header, return header, got your bypass. These are automatic air valves. I don't think I pointed that out. Ball valves with automatic air vents. That's what we got here, right? So this is a less expensive application. It's not quite as complex, and this will work provided that all of these loads are fairly stable. So remember I was mentioning the temperature, the load variance, if these are all pretty much staying the same, in other words, these return temperatures are all staying the same, this thing, and the fluid temperature hitting this evaporator is within its design specification, this thing will run just fine. Okay, it's just fine. But it will not work very good for applications where you have a big temperature variance, because what will end up happening, this is a service tip. If you have a chiller that's perplexing you and you're new on the site, first time you've seen it, and you can tell that this thing's plumbed as a once through, and intermittently this thing's tripping out on high head pressure, coils are clean, you did all your stuff, you don't have your glycol mix is good, your fans are all blowing air, you got, the coils maybe a little dirty, but not too bad, but intermittently it's just tripping out. And when you gauge up on it, look on the readouts on there, it's running normal pressures when you're there, even on a hot day. Okay. The way this will happen is a customer makes some kind of a change. And I can't tell you how many times this happened. Let's say on this condenser or methanol heat exchanger, some dude downstream somewhere opened up a valve and dumped in a crap ton of heat into this one heat exchanger, which immediately hits that evaporator. What happens to your head pressure?
What?
Yep, goes up. So that's the kind of thing that will cause a problem for you, right? So whenever you run into situations like that, what I used to do is ask the customer right off the bat, so this thing's been in here running 5 years, have you guys done anything? Usually you get, no, it's just fine. Sometimes what we had to do is we would put data recorders on here and just let them hang out for a couple weeks, and that would catch it, because the data recorder would usually pick it up in a cycle, right? So that's something that yeah.
I had that exact same scenario once, and there were actually flow meters on each of the branches. It was in a metal stamping plant where they had a bunch of machinery. The whole plant shipped over from Germany. They only had a 5-degree temperature drop across the chiller, all kinds of heat coming out the condenser. Everybody was saying that it was low on charge.
Yeah.
Running all the way up in RLA, and none of the flow meters are reading anything. And the whole thing, it's always the electrical engineers that get
Right.
my skin. They hate being told what to do. They're smarter than us mechanical people.
Really? Yeah.
You walk down balancing valve all the way out at the end, and ball valve.
Yeah.
And I said, "You got a ladder handy?" I go, "Watch this." And I crank down on that ball valve. I go, "Tell me when you see that ball come up in its normal operating." This plant had been running great in Germany. They've been running for 3 years this way. And I put the ball, I go, "Tell me when that ball is right in the middle of that range." And I stopped. I go, "Now on the way back, we walk, and every machine, those balls were all in the right spot." We go back to the chiller, had our 10-12 degree temperature drop.
Yeah, the other one, I love talking shop. The other one on these systems here that that's we had this happen more on once throughs, is if you make any change along any one of these valves right here, right? And you don't play around with this bypass. If this a lot of them don't even know it's there. A lot of times these are put in places where nobody knows they're there. But if you make any change along here, what does that do to your net flow rate going through your evaporator? Changes it. That's right. So the other one they'll have a problem is when nobody knows this is there. They don't make any change, and they shut down 1, 2. Maybe they leave this one open. They cut back. So then before they know it, they don't know this is happening, but all of a sudden this thing goes out on low suction, right? Because what happens is just like any refrigeration system, if you cut off load immediately by lack of medium moving across it, your TXV valve is gonna say, "Whoa, my superheat just took a dump," right? So it's going to start adjusting that TXV to get your superheat right. Well, in the meantime, that low pressure safety is sitting there looking like, what the hell is going on? As soon as that thing times out, bam, it goes off, right? So that's why, again, just like you did, right? You want to go along there when you get a call and everything out on this machine is pretty solid. You don't see a lot of issues with it. Usually what it is something that's something that's happened external to this machine. It's not the machine, it's something external to it. So very, very, very common on a once through, not so much on a recirc. So Any other questions on that?
Two gauges on the blue and one gauge on the right. What are the two on the blues?
Yeah, it's hard to see it. This is a flow meter. We just the CAD program we used. You talking here and here?
Don't have a symbol for a flow meter.
Flow meter, okay.
Flow, yeah. This would just represent a rotometer, but rarely we. I used to put these on every one of our drawings. We never got them installed, but we always put them on there, right? Okay, so that's that. Okay, so let's get into some stuff here. Let me look at something here real quick. Yeah, I don't want to get this overcomplicated here. We don't have enough time really to. Okay. All right. So I'm going to call an audible here. How you guys doing on time?
Good, you can go as long as you want, really.
Okay. Okay, cool. All
Another
right. So what I want to do is I want to go over sort of the gold standard, if you will, on how to size a chiller. I'm going to go over this part of it, and then if we have time, I'm going to pop over into the system sizer tool a little bit. Okay, let's see.
One question before you get started.
Yes, sir.
Can you please define approach the way you were using it?
Yeah. I know I've got some refrigeration guys. So the approach in process chiller world is the fluid of the cooling medium as it's entering whatever we're cooling. Now, I do know there's also a term in refrigeration that's similar. And yeah, that's the way it was taught to me.
There's evaporator approach, condenser approach.
Yes, yeah. Yeah, when we're in the process chiller talking about the fluid side, talking about the hydronic side, when a customer has 50-degree fluid requirement going into their process, whatever the heck that is, our term for that would be it would be a 50-degree approach. But yeah, I've had more than one refrigeration guy look at me sideways when I say it that way. Okay, so real quickly here, when you know the capacity of the chiller, you're going to go online, and I don't know if you guys are going to do it, but the way you want to, what you want to do is you want to look at the specifications, and I'm going to give you a few speed bumps to be careful about. Okay, so this is my old company that I sold. This just happens to be the guy I sold it to, his website. This is a live website. Okay, so we're just looking at a packaged air cooled with integrated tank. This is we sold these things a gazillion of these. Has a little package. It's an air cooled unit with an integrated recirc system. So it has 2 pumps in it. Anyway. So one of the things I don't want to go too far off in the weeds here, but these are the capacities. And one of the things that ran our customers into trouble from time to time, even engineers, believe it or not, is the capacities that are rated on these chillers are based on a very, very specific standard. And it's the ARI standard for process chillers. And that ARI standard is 45-degree approach. So that's 45 degrees leaving the chiller going to the process, 95 air-cooled unit, of course, 95-degree air entering the condenser, right? So anything off that spec, these numbers go out the window. So for example, if you had a customer that can deal with a 60-degree approach, and it's, let's just say, for example, it's a 5-ton unit. Okay, so let's just say, for example, it's a 5 horsepower unit, This is a PZAT 5S. At 45 approach, its design is fit. This is actually, it gave more than that, but anyway, 55,200. But if you jack that up to 60, you're going to get close to, I'm guessing now, 80,000 out of that same chiller, right? And vice versa. So any number off of that can cause a change. So that's probably the main reason why I wanted to show this to you. And usually in the specifications somewhere on the capacity tables, it'll tell you that. But that's a really, really important thing to understand. We have a few customers that screwed that up. All right. So this is a capacity table. So if you wanted to buy a chiller, if you ever, like, if you're selecting a chiller, let's say you get a customer, our brewery again, and you say, okay, I want to replace it. I want to give them a quote on a chiller, and you happen to be the guy in the office and you're trying to figure this out. Get a hold of the manufacturer, and I highly recommend always asking for a capacity table on the chiller. And you should get something like this. It'll give you the, I don't know if you guys can see this. This is pretty small. It'll give you, this is a ZB5. This is a Copeland scroll. It gives you the capacities, the tonnages, the KW and the EER at different leaving temperatures going out to the process, as well as different ambient temperatures entering the condenser. So, and then it usually gives you in a couple different table forms. This is the compressor stuff, but this gives you, gives you a good graph to tell you what you're dealing with. So now, one of the things that also you need to keep in mind is the compressor is always going to be rated on suction temperature. So the saturated suction temperature is always going to be around 10 degrees colder than your fluid. So this table here, and this is the way we did it, but a lot of manufacturers do it the same way. This table kind of cheats, and it gives you what the capacity is. This table here is actually giving you what the compressor will do. So for example, if you have 45 degrees, if you have 45 degrees going to the process and it's 95-degree ambient, this cap table here will give you, it'll give you 6.8 tons. Okay. All right. But if you wanted to look at it on the graph down here, you have to convert it to saturated suction, because that's what this ZB858K compressor will do. So in simple terms, we have to drop our suction to 35. So here, and then this is your ambient temperature. So 35 and 95. So that compressor is capable of giving you high 70s. Okay. Let's see if that's right. So 95 ambient, yeah, 78,900. That's what I would use to size this unit. Does that make sense?
Totally.
All right, that's where I usually lose everybody on that one.
Anyway,
Anyway,
capacity drops off. If you go from 45 degrees down to 10 degrees, it's more than half less.
it goes down. Yeah, it goes down a lot. Now it'll vary depending on
It has to do with your compression ratio on your
Right.
compressor.
Yep. And that's just not process chillers. That's just how they operate, right? Any refrigeration compressor does the same thing. But anyway, so when you're sizing a unit, just make sure that you really give a close look at these capacity tables if you can get it. And I'm going to tell you right off the bat, you call somebody over at Carrier or Train. I don't mean to pick on those guys, but you get a typical counter guy and you try to have this conversation. A lot of them don't know. The other thing is that, they'll tell you some information, but I would always check it. I would ask them, do you have a cap table on this machine? Yes, great. Can you send it to me and make sure you understand it? And if you don't, send it to me and I'll help you out. I still get calls. I still get calls to this day from engineers trying to figure out what the heck some manufacturers doing. Anyway, I digress. Okay. So that's a submittal lookup and that's the cap tables. Before we jump over to the tool, so we've been at it about an hour now. You guys, I'll stick with you on this. You guys want to keep going?
Sure.
All right. Very good. So let me get out of this. Let me get over here. Okay. So this is the tool that I developed years and years ago I actually designed it for engineers, but I've got a lot of really smart contractors that I gave this thing to over the years. So like I said earlier, this does not negate the need for a qualified engineer, but this will get you in the ballpark. So it's a real basic thing. You have to, this will run on any machine that's set up with Excel.
This would be perfectly acceptable to use when we're backwards engineering systems that are already in. And
Yes.
we have to explain why they're not working.
Yeah, I've got a lot of people that did that. Yeah, especially you're going to see some of the stuff this will do. It's pretty cool. All right, so this is the home page, real basic. You have just the basic navigation here. You can click these big buttons here, or you can click these tabs, doesn't matter. So the first thing you get to is the site. You enter all your site information, whatever, it depends on how you want to do that. So the first thing that really requires to make this thing work is you have to go to the conditions tab. And the conditions tab just is basically going to ask you some really basic information. So for example, what's the coldest outdoor temperature this thing's going to run into, right? And you'll also notice that there's these little red, you may not be able to, let me make this bigger. Let's see here. Yeah. Can you see that okay?
Yeah.
Okay. So there's these little red triangles here with the question marks, and this will kind of give you, like, if you're like, well, what the hell is he wanting to know here? So you just roll this over and it'll kind of give you a real brief explanation of what System Sizer wants, right? The only two things that really have any impact to do on the chiller sizing, which I'll show you in a minute, is 1 and 2. This is just basically here to help us know what kind of voltage the customer wanted, and we didn't do a lot of 50 hertz. So anyway, it was just a data point for us. So I'm going to,
You need at the end.
what's that?
The customer would say, oh yeah, I got 460, I got 483 phase. But by the end of the calculations, because he's trying to cool maybe makeup air or something like that, you get to tell him how many amps he needs. And you're like, oh, okay.
Yeah, well, you're gonna take, yeah, okay, I'm glad you said that. So you're back at the submittal data then, right? So once you make your equipment selection, then I keep looking over here to my other screen. I don't know why I'm doing that. Let's see, let me make this a little bit smaller. There we go.
5 volts is Canada.
What's that?
Number 3, 575 volts is mainly Canada.
Correct. Yep. Yeah, we did a lot of stuff up in Canada too. You can't for 50 hertz. I would not use this for 50 hertz because that's your whole calculation for your capacity changes when you go from 60 to 50. I'm sure most of the compressors and everything will run at 50 hertz, but your capacity is much different.
380 is China, India, Japan. It's 220, 380. It's really 381.
Yeah.
So Martin, looking at your coldest temperature, you had three choices there, 50, 40, or 30.
Oh, it goes down from there probably.
Did you have a lower ambient than, okay,
Yep. Yep, and I'll show you what this does here. We'll play with this a little bit before I save this out. Okay, the other thing we're going to do is we're going to say what kind of glycol we need, right? So you guys are what, Ohio?
yes.
Yeah, okay. What do you
40%.
guys run? 50?
40% typically.
Okay. All right, great. All right, so that's basically it. You just need to make a statement here. Don't worry about the voltage. So now we're going to go over to the process input, and we're gonna put in some stuff. Now, basically what you're looking at here, guys, is a loop, right? It's just done in a little different way than what we were looking at before. So you got your little chiller here, you got your supply header, you got your return header. Branched off the supply headers, you have these here, and then it goes through the load, and then it goes back. So that's it. That's all this really is. So really simple. You know, you can have up to let's see, can that let me do that? Oh yeah, so I guess it will let you do that. Anyway, so you can name the loads if you want. I never did, but and what you want to do is you can do up to 3 loads, 3 different process loads. That's all we do. This was a free tool. I had guys say, well, what if I got 12 heat exchangers? I go, well, you know, do it 4 times. I don't know. So we only have 3 loads, but for, you know, for a lot of systems, this works great. You're going to declare your GPM, and this is all on a drop down, and we do that to make sure that we get the data correct. Your temperature to load, right? You're going to enter that, drop down in what you want. Estimated load temperature rise, right? So in this case, we're anticipating that we've got 55 approach. So we have 67 leaving, coming back into the red line here. Your pressure to load. So this load, what is required for pressure? That a common place, as I mentioned earlier, you're going to get that off of your site prep guide for whatever it is you're cooling. Load pressure drop. A lot of times you're not going to know this. I would always use 9 or 10 pounds just to be on the safe side. You don't know. You're a lot better advantage if you happen to have a existing system, you're doing a change out. Tolerance range. So this could have been for an MRI. Matter of fact, I think that's what this example was for. Branch pipe length. So normally these headers are run at the top of the wall, and they run down. So you want to figure out how far from the header you're going to the inlet of your process, right? So that's going to be your branch pipe length, and then you're going to have your fitting count. Now you never know this really. So I put a note in here, select number of fittings for this branch. If you don't know, use 1 fitting for each foot of branch. That's just a good way to go. Because again, each fitting has an equivalent pressure drop. Okay.
10, 12.
Okay. Any questions? That pretty clear so far?
Yes.
All right. So then what you do here is you're going to declare the distance between the chiller and your load, your first load, and then if you had other loads, right? The other thing too, I want to let you know is that some of these are grayed out. So typically on a process load, you're only going to have one temperature going to all 3 loads, right? So if you change this to, to 60, it's going to assume that those are all 60 as well, right? And the same thing with the tolerance, right? So the tolerance would be about the same. So that's why these are grayed out. You can't input yeah.
If those were all equidistance, like under number 2, we'd be down to branch pipe length 20 foot, and then number 3 down there would be like 30 foot.
Yeah. Yep. Yeah. So it would be 50 would be 50 feet from the chiller to the first one. And then let's just say this is 20. So this would be 20 feet from load 1 to load 2. And let's say that, so it's going to be from its left, right? So you're going to add it. These are additive based on the distance between each one of these. Does that make sense?
So are you
Like
saying
50,
70
70,
feet? Saying 20 feet from the load 2.
Yeah.
So-
So right, if load 2 was 20 feet from load 1, then you put a 20 here.
Oh,
And then if load 3 was 20 feet from load 2, you'd put another 20. It's the distances
Between the loads.
between the loads. Yep.
no, I got that wrong.
Yeah, I'd have been in the 150 range or something.
50, 70, 90.
Yeah.
We can play with that. We can put another load in here in a minute. Okay, so the last thing is going to be your output. And so basically what it's done here, it's the same layout. It's the same layout, except it's done the numbers here. So you got 108,000 BTUH, your KW is 31.65, your tonnage is 9. It gives you all the data here. Some of it you probably don't care about. It also calculates what it recommends for your branch pipes, as well as your header pipes. So it's, and this little guy, it's recommending 1.25 inch pipe. And it's giving you along the way, it's giving you what your GPM is going to be, your net GPM. Now, yeah.
Well, your GP determines your pipe size based on
Your flow
standard.
rate. Flow rate
rate.
and flow rate and the number of fittings.
So we didn't even have to put in the GPM, it figured that out for us, and then
Yep.
it'll go on the pump.
Yep. So down here, it's giving you your all your so you're going to use all this stuff to base your design on. And I'm going to point out some things here, very, very subtle. Okay. So you'll see that the load, even though here it says 108,000, right? But it's recommending 115,000. Anybody got a guess on why that is?
108 is probably not a standard size.
Temperature changes.
Well, remember back here, we played around with this a little bit. So it calculates the additional tonnage, the capacity loss from your glycol. That's why that number's out of whack. Okay. And it explains that right here. That's why that note's in there. It tells you why. You probably can't read it, but that's what it says.
Change them to 0% glycol and come back to the 108.
Yeah, should. Yep.
Beautiful.
Beautiful, that's it.
Martin, how do we get a copy of this program?
I'll just go ahead and send it to Tom. But wait, there's more. Okay. The other thing it does is, I want to point out here, and again, it's very, very subtle. See over here, we declared pump capacity, or it's telling us we need 19.8, but if you remember, back here, we only needed 18, right? Why do you figure that is? It's sort of a test.
Heat exchangers
Nope.
Fitting.
on the
Pump curve,
chiller.
What did I recommend that you put into all systems?
Or your strainers,
Nope.
your flow meters.
Bypass.
Okay.
You want to always have a bypass at the end of the run. So if some monkey down the road shuts off the valves to your loads, especially if you have once through, you want to make sure that you got a bypass installed to at least make sure that you got a little bit of flow going in to your going through your pump. So it calculates that. It also calculates your feet ahead. So these are basically what you need, right? Huh?
At 1.1 multiplier.
What, I'm sorry. Yeah, it does your PS, right. It does the pump head to PSI conversion automatically. Now, one of the things I want to point out here too is if you make these adjustments, so let's run our glycol back up. See what it did to the head? It jacked the head up because of
Specific gravity.
Viscosity.
the delta P. And it'll also recalculate if you drop your set point, it also recalculates your feet of head based on the viscosity. So because it gets colder, it's getting thicker, right?
Yes.
Now, the other thing, this other stuff here, this is sort of brand specific, but when you were over here and you put in your conditions, you know, this is why we ask you that. How cold does it get outside? And we said 50, right? So you see here, these were options that we offered. You know, variable fan speed, you really don't need it. Flooded condenser, heated flooded condenser. Yes, we recommend, because you're running such a high percentage of glycol, we would have upsized that evaporator, more plates in it. And then, so anyway, it makes recommendations. So if you were to go over here and you were to drop this ambient down to minus, let's go 0, you'll see it changed these recommendations. It's recommending now that you have flooded condenser with a heater on the receiver, right? So it's making those recommendations. Now, I don't know if the manufacturer offers those or not. But that's I know my old manufacturer did, but you know, anyway, some not all chiller manufacturers will offer these features, right? So anyway, that's the brief run through on this thing. Hopefully you guys can, you know, use it. It's what I was telling Tom before. What I used to do is we had some high volume customers, and they just had this spreadsheet, and they would input it. That's why we had this little quote sheet here, right? And as you're filling out all this stuff, it's populating this quote sheet, and it would we could go right into doing a design for a customer from this sheet here. So do you guys, if you guys want, I can put in some more numbers here, but I'd suggest, and it's running a little bit behind, we're running pretty late, but what I can do here, I'll send this over to Tom, and you'll have this recording, and you know, check it out. And if you have any questions, give me a holler.
Awesomeness.
Cool. Well, guys, you know, I'd like to keep in touch with you. I don't know if you've checked out my new venture. I'm going to do a little shameless plug here. So I'm doing skilledtraderescue.com. So if you get a chance, check this out. I have ebooks, and I've got a lot of really cool stuff in here. We have a workshop. If you know anybody, this is free. If you guys have anybody who wants to do this this workshop, and I'd encourage you guys to check it out. Basically what it is, it's a success plan for skilled trade techs. So we don't get in any real you know, technical troubleshooting or anything like that. It's more you know, the habits to be a well-rounded, balanced work life, all that kind of stuff. So check it out if you get a chance.
Are you partnered with any vocational schools or anything like that out there?
Not yet. We just got this business up and running a couple months ago. and I published a book. It's a 4-book series, but I have this one called Technical Excellence.
I see
And
a definite need for that. Is it geared more towards guys in their first 10 years or their last
Yep.
10 years?
well, it actually we've been selling a lot of books, and the technical excellence thing can apply to any tech. I mean, I one of the reasons.
On there would be fantastic for just starting out. It's could totally change the outcome of where they end up 30 years down the road.
Yes, and like we get into money management, that's going to be one of I'm going over work ethics.
But they shouldn't be in high school.
Yeah. If you guys, any referrals you can give me to get the word out would be great. My new mission in life right now, I made all the money I want to make. I'm just trying to give back, and I want to help the next generation. I'm going to help them avoid the mistakes that I made. And I tell everybody, I never went to Harvard Business School, but I know for sure I paid the tuition a few times over. But anyway, yeah.
Give me a call sometime, daylight hours tomorrow for you.
What's that?
Give me a call sometime tomorrow morning
Okay,
when you're up and about.
I will. Is that Tom talking?
Tom,
Okay, yeah, cool. Sounds good, guys. Well, I will go ahead, Tom. I'm going to email you the Excel spreadsheet, and if there's anything else I can help you guys with, great questions. I really appreciate it, and it was it's just a lot of fun doing this stuff.
Do me a favor and include your snail mail address in the email.
Okay,
I'm gonna send something to you.
yeah, we'll do.
All right.
Perfect, guys. Have a great night. Drive safe out there.
Thanks,
All right,
Marty.
thanks, Martin.
Take care.
Bye.
Bye.
I could have used that tool before.